Thank you so much for inviting me. I'm really delighted to be here. Thank you for the general invitation. I love Cambridge. It's wonderful to speak here. Okay, so I want to plunge right in. This is about, I want to show you a Bayesian non-parametric approach to multiple regression. You have one Y, you have lots of X's. It's remarkably hard, I think, to do that sort of non-parametrically. And I'm not a subjective Bayesian. Okay, I love Bayes, I love frequency. I really think that most good procedures are pretty close to a Bayesian procedure, but for me the miracle is just to watch how the Bayesian machinery can work once you set it up properly. So that's kind of what I want to show you. This is joint work with Hugh Chipman, Rob McCulloch, Matt Pratola, and Tom Shively. There's 4 papers in here. The first 3 were Hugh, Rob, and me, but then we'll sort of go on. I'm going to tell you about general BART, and I'll show you some other extensions to monotone BART and heteroscedastic BART, which further attest to its remarkable flexibility. Okay, let me start off here. I'll stand back a little bit. So I don't want to get in your way. So look, it's the basic regression problem here where I have, get this pointer right, okay. So I have one Y and I have P X's. The most important thing is just this setup, and I'm interested in drawing inference about some function. By the way, there's a lot of room for theoretical development here. Some people are beginning to get properties, for example, showing that this will all work when F is Holder continuous, whatever, but there's a lot more to be done. And so you can be thinking, wow, what aspects can we theoretically improve on here? But I'm just going to try and convince you that this works remarkably well. The Bayesian ensemble idea is simply to approximate your unknown function by a form of this kind of a form, where it's the same function, but they're different parameter values, and the parameter values come from some prior distribution, they're IID. And what we're going to do in this is we're going to use the posterior of F for Y, just for given Y for inference. And BART is a special case of this. It works remarkably well when each of these G's is simply a regression tree. So I'm really going to approximate this model by Y is the sum of regression trees plus noise. And one of the key calibrations in this whole thing is to set, using Y, to set your prior so that the variance of this amount is in the same neighborhood as the variance of Y. When we first put this thing together and we were trying various things, it was hopeless. It didn't work. We thought this was just kind of a lark. And all of a sudden, we hit upon this calibration of using Y. This is kind of informal empirical Bayes, but to calibrate it so that this variation was comparable with that variation, and all of a sudden the thing just took off like crazy. In a way, it has to do with the likelihood and the prior being compatible. If the likelihood's here and the prior's really too dispersed or in the wrong place, the Bayesian method can't work. But as long as they're sort of close, Bayes seems to work remarkably well. Okay, so to start, I said each of those ensemble components was a single regression tree model. And you're probably all familiar, this is CART, but when we first started working with this, we developed something called Bayesian CART. We wanted to take the original CART algorithm, which was really just a sort of recursive partitioning of the predictor space in such a way that you would sort of divide up the regions of Y into homogeneous regions. And we wanted to turn that into a statistical model. Why did we want a statistical model? So we could have a likelihood, because once you have a likelihood, then you can start doing Bayes. Okay. With no likelihood, too bad. Anyway, so the parameterization I'm going to use for the single tree model is simply, I'm going to let T denote this tree structure here, and M denote these bottom node means, and then G is going to be a function that given a particular x, and you drop an x down, so if x is less than c, x5 was less than c, and x2 was greater than d, you would assign y a mean mu. It's just a step function. It's real simple, okay? Okay, and I'm using normal errors right now. All of this extends, in fact, we're finishing a paper using Dirichlet process errors, and no problem at all. Okay. Bayesian CART, okay, which is what we developed that single tree model for, was simply, let's just add a prior to the unknowns, the bottom node parameters and the tree and its splitting rules, okay? So we devised a particular prior, and really what you have to do is first you put a prior on the trees, and then you put a prior on the bottom node parameters given the tree, and we just put a simple normal prior here, coupled with the normal error. This all becomes conjugate, and you can integrate stuff out. In fact, for the tree process prior, we put a stochastic process here which generated a tree skeleton plus uniform prior on the splitting variables and splitting rules. The idea was you flip a coin and you get a split, you flip another coin, you get another split. Now you have to do assignments to various things. And then we were able to derive, because of the conjugacy, a closed form for the posterior on the tree space given y. And then we used Metropolis Hastings to sort of do a proposal which would randomly search through the tree space and converge to the posterior distribution. So it worked quite well. Imagine, by the way, in this, this is just one example, but if I had p variables, how many possible tree models there are. So it's just huge, and you're trying to sort of go through some huge space. Okay, well, there's something I actually didn't like Bayesian CART, and the reason I didn't like Bayesian CART is you would start someplace and you would start searching the posterior, and you would converge so quickly, good news, to a single mode and get stuck. Really bad news. So what would happen is basically the only way to sensibly search would be to keep randomly restarting at different places and getting different trees, and then it was a nightmare. What do you do with all of that? Average them, etc. So I wasn't so happy about that, and we tried various things. We tried treed models where we put regressions at the bottom nodes, but we ultimately ended up with BART. And this was also kind of a lark. We weren't sure this was going to work at all. We had seen some stuff that Jerry Friedman did. And the MART stuff, the gradient boosting, and we thought, why don't we take a Bayesian perspective and see how that works. So here's the BART ensemble model, and you can really see what it is. It's taking y, and now it's the sum of the trees, okay, plus the error, and each one of these represents a tree. So at the bottom of each tree, there's a constant, right? Each of these g's gives you a single constant. So that means that the expected value of y, the regression function, given all of the parameters which determine the trees, is just a sum of bottom node mu's, each of which eventually, by the way, are going to be given a normal prior. So this is just the sum of normal constants. It's really a very simple model, okay? In this, the number of trees can be much larger than the sample size. So we do examples with 200 trees and 100 data points, and it works just fine. Part of it is using a strong but neutral prior on all of this. But you can think of all these G's as a highly redundant, over-complete basis with many, many parameters. Okay, so it's a bit insane, but we're trying to think sort of large and seeing what we can do with Bayes. And the way we can manage this is this is now part of the model, okay, is a regularization prior. I like calling it a regularization prior so there can be initially I called it a technological prior. I just didn't want to call it a subjective prior. This doesn't represent any information that I have, really. But what we're going to do is apply that Bayesian CART prior to each of these parameter pairs independently to make each tree small, okay? So when you flip the coin, the chances of getting tails so you stop growing is large, and making each mu small so that so that basically it's a normal distribution, and we're going to make the variance of that normal prior quite small. And then the observed variation of y is used to calibrate the choice of the hyperparameters for the mu and the sigma priors. So this is kind of a violation of the coherence. We're just trying to make a machine that works. Okay? And I call it a regularization prior because it simply keeps the contribution of each of the g's small, explaining only a small portion of the fit. Okay? You want to model fine structure. And to model fine structure, you can't let any tree get too big, because all of a sudden you can't sort of get the fine structure. More about that, I'll show you something in a second. Just some connections to other modeling ideas. This is a lot like Bayesian nonparametrics. Basically, Bayesian nonparametrics, they put in tons and tons of parameters to get all kinds of flexibility. And then they will use a strong prior to shrink towards simple structure. That's the regularization. And what BART is doing is shrinking towards an additive model, but there's some interaction. Notice I should have mentioned each tree model is really kind of a little interaction model, because we saw before it split on x5, but then given x5 in a certain region, x2 did something. So this thing does model interactions. Okay. This is, for me, I think this is one of the absolute coolest things about BART, is that each of these basis elements are dimensionally adaptive, okay? They're random basis elements. And notice sometimes people will say, I have a random basis, and what they'll mean is that, well, I took a wavelet basis, and then I put random coefficients on the wavelets and sum them together. There's no coefficients that are multiplying things here, okay? All the action is completely in each of these basis elements, and it's the bottom node means that can change, and the trees can get big and can get small. And we'll see when we do the MCMC for this, we watch as this model fits. Some of the trees are growing and getting shorter and whatever. I mean, it's like a little snake going through and really, really adapting. And it moves so smoothly through the space. To me, it's just amazing. This also has
a stupid question.
Sure.
Isn't a sum of these trees just a tree?
Let's see. Yes, you could represent a sum of the trees by a tree, but what we want to do is you get much more flexibility by having a sum of different ones. If I wanted to ultimately get to, maybe I should say a sum of trees isn't a tree, because you can think of each tree. Here's a way to realize that they're not, even though you could sort of represent it. Each tree represents a partition of the X space.
Yep.
And now, if I had one big tree, I could get one huge partition, but there'd be one bottom node for each of those. Whereas here, I'm now going to take one partition and then add another partition and step functions there and step functions there. So really, at many of the X's, I have the sum of lots of mu's. And
so it's a reduced number of parameters.
Well, it kind of reduced number of parameters. It's actually particularly good for modeling functions which themselves are the sums of low-dimensional components. But yeah, so it's slightly different. This certainly, by the way, will, from a computing point of view, just mixes phenomenally well compared to the other thing. But if you had enough time, you could probably do everything that we're doing with a single tree, but it would have to grow so deep and really be so unmanageable. So, great question. Okay, this is the theory part of the talk. This idea, right, is the fit becomes the cumulative effort of many weak learners. Here, right, here's the famous George in the Park painting of Surratt. This is pointillism, and so there's lots and lots of small little specks, but all together you're really able to model the whole structure there, and remarkably so. Okay, and you really need them to all be, tiny specks in terms of what you're doing. If you didn't have this regularization prior, which forced every tree to be small, all of a sudden one tree could take up way too much of the variation, and you wouldn't fit this kind of fine structure. Here's a sketch of the algorithm, and it's nothing more than Bayesian backfitting, okay? What we do is we have an outer loop, which is a simple Gibbs sampler, and what you do, you sample each set of parameters given y and all the other t's. So you just do one tree at a time, conditioning on everything else, and generating these priors. And then once you've gone through one loop of that, then you just sample sigma given y and the rest of the trees. In doing this, when we do one tree, given all the rest, what we can do is we actually, and this is what's said right here, is you subtract all the other trees from y, and now you're left with y minus the fitted trees has some error. You just drop off a tree and you regenerate a new tree. So it's as if at each step you're just doing a little incremental improvement, but this enables it to sort of creep through the parameter space and not get stuck and really mix well. Okay, and what we do is we, as I said before, we integrate out M to sample the T, and then sampling the T we do by, and then sample M of T, and we do that by using this Metropolis Hastings in Gibbs step. So this is how we compute the thing as we're going along. I'm just showing you a birth-death move, but lots of moves. It's very interesting. Matt Pertola has some very interesting move of shifting, splitting rules and moving things around. You can think of it hanging, and one way of taking a random walk on trees is you sort of pick it up by a different juncture and move things around. So there's just a lot of interesting aspects to do, and I'm sure we haven't done all of them. But notice this one here I'm showing is I've done a birth, added this, I've done a death, I've cut off this. Okay. But as the MCMC runs, each tree in the sum grows and shrinks, swapping fit amongst them. Okay.
Just a question. So what is this matching of this empirical base matching of prior variance and y variance happen exactly in the algorithm?
Okay, that's not in the algorithm. Once we've set down our prior and we've picked our hyperparameters, which have been chosen according to what y did, right? So now it's set up. Now that you have implicitly a posterior distribution.
So this is already implicit in this.
Yeah.
So isn't there a way to trade off this tuning of prior variance and y variance with the choice of M?
Oh, yeah. So what happens? As usual, great point. What happens is when you want to tune the variance of the mu's to the variance of y, the variance of y is really going to be m times the sigma squared of the variance of the prior mu's. So when you do this tuning, what will happen is the expression we use is as you increase the number of trees, the prior variance on the mu's goes down.
But the variance of y is observed, so
the variance of y
doesn't depend on M. So
the variance of y doesn't depend on m, but the variance of f depends on how many trees you have. So what you're going to do is you're going to allow each
but you
mu
can
to
sort of
only go.
trade off the variance of the normal with the number M.
You know what, I promise that I'll talk about it at the end. I have a slide at the end which has a sketch of the prior, and you'll see it more clearly, okay? But you're certainly thinking in the right direction. Okay, so here's how we move the things around. Once I've now moved around this space and I've got this implicit posterior, and what I'm trying to do from this implicit posterior is sample. And so every time I sample, each iteration through this whole thing is I get a draw from my posterior. So I've drawn new trees, and with these trees I can get an f of x value. And so now to estimate f of x, what I do is I just average all my draws at x. Okay. In fact, what I'm doing is I'm sampling from this posterior, and at each x value, I'm getting the posterior distribution of f. Okay. And what I can do is I can take the average as an estimate, but I can also get posterior uncertainty by looking at the variation around each point. and I can just take the middle 95% values, and that'll give me an HPD region, okay? Now, fair enough, I'm not sure that this is 95% in any frequentist way, although it does look like it works out pretty well. But it tells you the kind of, in some sense, the right function. This is the right functional form for what's going on. And I'll show you an example for instance, when you don't have much data, these intervals will expand, and when you have a lot of data, they contract and get smaller. But let me,
Just a quick question.
Yeah.
Is it 95% in the Bayesian sense?
In the Bayesian sense.
Because you've calibrated the prior, though, using the data, so it seems like there's some empirical base going on in some sense.
Sure, I suppose there's that. And also it's a regularization prior, which doesn't really represent anything as well. So yeah, so there's various rules of Bayes that are being broken. But it is that, at least you can get, in a sense, a relative sense where things are. And I'll show you some examples that are somewhat compelling, but fair enough. Okay, this was just an example. This was kind of proof of concept. Is we did they call this a bake-off in the I guess the machine learning world. We looked at 42 data sets, somebody else's data sets. So thanks, Wei-Yin Lo, and that's actually the uncle of Po Ling. So what a good guy. Anyway, here the data sets, P went from 3 to 65, not so huge. There's N, but for each of these data sets, we did a sort of 5-fold cross-validation. So then we were seeing how well 80% we could predict the remaining 20%, and just ran this big thing. And what these box plots are just performance, the performance of each of these methods. What we did is we took the very best method and we divided the RMSE of all the other methods by it. So if it got a 1, it was the best. And if you got a 1.2, it meant you were 20% worse than the best. And you can just see, here are the two BART, here's boosting, here's neural nets, here's random forests in this, okay? And you can see certainly that the BARTs are doing well. One thing I hadn't mentioned yet is there are hyperparameters that we tune to Y, and we have a default tuning. So if you just want to use this out of the box, then you can use BART default, and BART default does remarkably well. You don't have to do any cross-validated tuning. Whereas if you do cross-validation, you'll do a bit better, but then that takes some work and some knowledge on a user's part. All of these methods, boosting, neural nets, and random forest, take, you have to sort of carefully calibrate so that they work. Okay. Here is now a first picture of taking a specific instance. This is a simple simulated one-dimensional example. Okay, obviously there are many ways to do the one-dimensional example, but this will sort of show you that it's working correctly. So this red is some true function. It's a parametric function, but I don't need to tell you what it is. And we generated data from it. And then we applied BART to this. And if you apply BART to this, you can see that what you get is the blue line is the posterior means that we've drawn from the posterior. And also this gray is the 95% HPD region. So it's giving you a confidence region. Notice it's interesting that you're sort of fitting the line better, of course, where you have more data, but you also have much, much smaller uncertainty intervals. So it's kind of doing the right thing. But yeah, I don't know if it's 95% in the long run. Absolutely. Okay. I'm going to tell you, this is MBART, which we're going to see a bit later. This is monotone constrained. So you can see the fit is actually monotone here, and you actually get smaller intervals. That's coming up. Okay. I thought it'd be interesting, I don't want to take too much time with this, but to show you a simulated data set. By the way, I have 60 slides, but some of the later slides are quite sparse, and I can show you. So don't worry. So here this is just a function that actually Friedman used 100 observations from this to illustrate the potential of Mars, multivariate adaptive regression slides. So we just took this. It's a nice nonlinear function, and it also has the property that the last 5 coefficients are exactly 0. Okay? And we generated the x's from a uniform distribution to get our data set. If you try this, if you try random forest neural nets and gradient boosting on this example, BART really does substantially better. But that's just one example. Okay, but I want to show you, if we go back here, this is a one-dimensional example. Okay, but how do you sort of show in high dimensions? How do you get a picture of what the uncertainty is? Well, for this model, here's an example of running BART. I've plotted my in-sample f of x, which I can compute exactly because I know the function, and then I've got my BART estimates here on this axis, and you can see where the points are, and the lines around those points are showing you the uncertainty intervals around there. What's kind of cool is you can generate, after you've used a sample to fit your data and get your set of trees, you can now apply those trees to a second independent sample. So it's out of sample, and you can look at your out of sample performance. And of course, you get your posterior there too. And so this is like, semi-supervised learning. And here you get to see, look at how much larger these intervals are. So you get a sense of out of sample how it's doing. This is a plot of the sigma draws. As you're going through the MCMC, you're also drawing sigma each time. And that can be useful. That can be useful for sort of gauging, has this thing converged once this thing sort of gets steady. Of course, it's no guarantee, because it could at some point move to another part of the space and jump, but it seems to be quite stable. This is with 100 trees. If you try to do this with one single tree, what happens is you just can't get all the structure there. So one tree just seems to be challenged and somehow just stays away. And so we find this out. I'm not going to show you any of these added tree plots, but you can see that as you add more and more trees to the model, you quickly get down to a sort of sweet spot, which often happens around 50 trees. Anyway, this example, this is when Rob McCulloch first did this and showed me this stuff. I thought, wow, that's great. Since it's working so great, why don't we try it? Why don't you add another 10 x's? And he did, and it worked pretty well. And then I said, well, why don't you add another 95 x's? And he said, you're crazy. We've been drinking. And but he did, and it worked. And then he added 995 x's, and there's something there. So here's what happened. Okay, so this is now. We have 100 ops. I think this might be 200 trees, actually. But here, you can see the exact same plot before. This is with 20 x's. Here's with 100 x's. And you're still finding, you're finding 5-dimensional structure in 100 dimensions. And here it is with there. Out of sample, you can see that it's certainly worse. And in sample, it looks awfully good with 1,000 x's. But out of sample is not nearly as good, but you are finding something. And clearly, there's some structure that you're not getting because these are a bit high. But that's just to sort of show you. It's wonderful, all the kinds of inferences you can start thinking about with BART. This is sort of one of my favorite parts. One way you might measure variable importance in BART, and there are other ways, definitely lots of other ways to do it, but one way you might do it is you might count how many times you use a predictor in the trees. So for example, if I go through my trees, I can see how many times did I use x5, how many times did I use x2. You might think about weighting them, but we didn't do that. We just sort of did raw counts. So basically, the importance of each x can be measured by its overall usage frequency. Okay. This really works well when the number of trees m is small. If you have too many trees, it's too flexible. But if you make it really hard for trees to enter, they kind of compete to go in. So here, basically BART is like a competitive bottleneck. So if I reduce the number of trees, say from 100 to 10, okay, magically BART kind of is trying to find the x's that are going to predict y. So it's an automatic attractor, but only those which explain why those which most explain why will be attracted most, keeping out the others. So then you reduce the number of x's that you have, and you can quite clearly distinguish between which you want. And here, let me just show you, this would be doing BART variable selection on the Friedman data. So here, right, here is, if I use 200 trees, it's this red dotted line. And this is just telling me how often variable 1 is in, 2 is in, 3, 4, 5. And I know that 6 through 10 shouldn't be in, 1 through 5 should be in. But as I now reduce the number of trees, let's say to 10 trees, all of a sudden I see these 5 and I don't see any of these. By the way, this is model-free variable selection. I don't know what the structure is. What I'm doing is I'm finding those variables which might have a relationship. And you can do things like partial dependence plots to begin to see what the structure might look like. So imagine this stuff sort of begins to, we often talk about model selection or variable selection, but what about model building? Model building, sometimes you start off and you have 1,000 X's. Where do you start? Sometimes you start off with one simple regression model and then gradually build to that. Well, this is a way of actually finding maybe a small set of variables that you can seed and start beginning to build your model with. Anyhow, okay, so that's the introduction to BART. Now I want to talk about monotone BART, where it's all kind of the same, but what we're doing is we're approximating the monotone functions by the sum of many single trees. Each tree is monotonic, and it's not hard to make a tree monotonic. So here are 3 pictures. Right? When you were first looking at a tree, right, you might look at it like this, but a kind of an easier way to look at it is to realize I just have x1 and x2 here, and what's happening is this tree is partitioning x1 and x2 into a set of rectangles, and within each rectangle there's really a different mean, so a 3D picture of that would show you that this is what it looks like. And in my answer to Richard, if I have a sum of trees, I have a sum of these things, and so I'm averaging them, whereas if I have one tree, then I just have one thing going on. Anyway, you can see I'm calling this a monotonic tree because it's going up in this direction and it's going up in this direction. Okay. So in what sense is this monotonic? Well, here's our definition, and there are many definitions for monotonicity in higher dimensions, but we're just going to say that, look, if I add an increment in one direction holding everything else constant, then the function's going to go up. This would be for monotone up, but it would be the same for monotone down. This is not deep to think about, right? If I wanted to implement this monotonicity in kind of tree language, whatever, I would just realize that this has to be below its upper neighbor, this has to be below its above neighbor, this has to be above its below neighbor, etc. So for example, the mean level of 3 to be monotone must be greater than that, and greater than that, and less than that. Okay. Why sort of do this? Well, as I'm going along for the prior, or even better for the MCMC way of doing this, you can just at each step make sure that you're satisfying this. So not hard to do. Here's the MBART prior. It's just the same prior as we had before, okay? But I'm going to consider only the set of trees where each one is monotonic in a desired subset of the x's. Well, I don't have to be monotonic in every direction. I could just be monotone in x1 and x2, and I can let the others be free. That's not a problem. And to impose the monotonicity, I'm just really going to truncate the prior. One problem here, by the way, is that you no longer have that conjugacy where you can integrate out stuff. So computing is a little bit of a bear, but turns out we have a new algorithm to do that. And I don't mean anything religious here. I call it the Christmas tree algorithm. But the idea is our old algorithm, you would go from one tree with all these bottom node means, and think of the bottom node means as ornaments, okay? And so it's a tree with ornaments. And what we used to do, our old algorithm is, when you go to your next step, you'd start over with a new tree, you throw away, and you generate a whole new set of ornaments, okay? Well, you realize you don't really have to do that. If you just do a birth step move, you really are only locally changing part of the tree. So what you can do is now use essentially the same tree, but just change a few of the ornaments as you're going along. And you can make this very local. And it turns out that you can really get a very good approximation. It's impossible in this amount of time for anyone to follow this, but it did take some time to develop an algorithm that would work for this situation. Anyhow, there it is. Okay, let me show you some illustrations. This is kind of just a fun thing to see. So here is a very simple simulated monotone example. Y is equal to x1 times x2 plus an error. Okay, and the plot of the true function here looks just like that. Now, if I just apply ordinary Bayesian CART to this, this is what happens. Okay, it's not terrible, but you know, it certainly violates the monotonicity, and if we knew it was monotone, we wouldn't want to do that. Here's a graph of the fit. If I just take the monotone constraint with a single tree, it looks like this. So this one is monotone, and it's better, okay, but it's not great. If I use BART, even without the monotone constraint, BART seems to actually quite well get to this, but it's not monotone. And if I put on the monotone constraint, then it's really very impressively smooth. So the monotonicity just, you know, exploits that smoothness, and you can do it completely with tree functions and model the fine structure. To show you something else that's interesting with the monotone BART, here is a little 5-dimensional simulated example. I simulated 5,000 observations, okay, and here, just to show you, if I make sigma, well, here's with the noise level is pretty low. Here the noise level is getting pretty high. And what you can see here, here's the RMSE. If I use BART or use MBART, I don't really get any improvement if I have a very, very high signal-to-noise ratio, because I'm not going to exploit things. But as my noise level gets larger and larger, the advantage of using MBART in terms of reduced RMSE can get quite dramatic. Okay, so I think people all of you shape-constrained monotone people know this, that you can really win if it's really monotone and you impose that regularity. You can improve your RMSE, and it's happening here. Now, here's kind of, this was a thing, and some of you have heard me sort of talk about this, but you know, I was sort of, there's something I don't like about having to know in advance if a function is monotone. So, so suppose we're not sure if a function is monotone. What you can do is you can deploy MBART to estimate the monotone components of a function. So any function can be decomposed uniquely into its monotone increasing part and its monotone decreasing part, as long as it's a bounded variation. Okay? And so you can actually discover this monotonicity rather than impose it using MBART. Let me just show you. Here's y equals x cubed plus epsilon. And I fit, the red is the BART fit, and the green is the MBART fit. And of course, here, you know, I knew what I was doing. But what I might do instead is I might say, look, let's take, I have y and x, and I'm going to create a duplicate column of x. So I have y, and I'm actually adding a dimension. And now what I'm going to do is I'm going to impose monotonicity up on the first component and monotonicity down when using the second component, and plot both of those. And that's what I've done here. And you can see that the blue is the monotone upfit, okay? And the red is the monotone downfit. And the sum of these two is now an overall fit using them. So I've decomposed, and of course, I mean, we haven't gone far enough, but the natural thing to do was to devise a test where maybe you would throw this out, but visually you can kind of see. But you can begin to think about that. Now, suppose we do it with y equals x squared plus epsilon. Well, here's the BART fit, but if I were to use monotone increasing, I get this green line, and it doesn't work at all, okay, because the function's not monotone. Sure, that makes sense, but look what happens if I do the up and down. All of a sudden, I've fit the monotone increasing component, and I fit the monotone decreasing component, and the reason I can do that in the 2 dimensions is because the up one is conditional on the down one. So I've really decomposed the 2 parts. So if I didn't go to 2 dimensions, I wouldn't be able to do this. Okay? And here, which I find is perhaps even more dramatic, is here is a sine function. And if I were to just fit this thing with BART, I'm going to get a straight line. It's just flat, because there's no monotonicity. It's all balanced here. But if I do it on the separate components, this is the monotone up component of the sine, and this is the monotone down component of the sine, right? If I add these together, I get the green line, which is following this like this. So this is a vehicle. I mean, think scientifically, and you can do this in high dimensions. So think of this is a vehicle where you can sort of find, I think, the regions where a function is, where a variable is having an increasing or a decreasing effect. Okay, so there's lots and lots to do here, and interest in finding more examples with that.
Excuse me.
Yeah.
I don't really understand exactly, because why isn't the monotone fit on the right just a straight line, horizontal straight line?
Because so I'm saying y is equal to g of, if you like, it's a function of 2 dimensions, and so in 1 dimension I'm seeing where is the up part, and in the other dimension I'm seeing where is the down part. Because I've separated the 2, I think it's because I can condition on x2 to get the increasingness in x1.
Maybe I can ask you at the end.
Yeah. I mean, I was kind of surprised. I mean, this is, if I just do a 1-dimensional fit and force it to be monotone, then I get this. But it's going to the 2 dimensions. So y is on x up and x down, and it kind of separates the 2. But yeah, we'll take it offline, but thank you. Okay, let me go to the part 3 now, the heteroscedastic BART. This is yet a further variation of BART, which we think is pretty stunning. Here, and this one is with Matt Pertola, the other one with Shively came on this, but basically BART, right, flexibly fits the conditional mean with the sum of trees. Now what we're going to do, and we're in high dimensions, H-BART is going to flexibly fit both the conditional mean and the conditional variance. For the conditional variance, we'll use a product of trees. Okay. But pretty, this allows for heteroscedasticity, but also we're going to model the heteroscedasticity, and it could be that certain variables, right, are explaining changes in variance rather than changes in mean. And if you try and hold the variance constant, then it could be that gets absorbed incorrectly into the conditional mean. Okay, so here's the H-BART model, okay, and it's just like before, f of x, but now instead of a constant sigma here that we don't know, we're going to have some function of x as well, and normal errors, or normal deviations there. And here, f is modeled by the sum of trees, and I'm just using going to be the product of, and these are also regression trees. So it's the same as a regression tree, but now each component here is multiplied to get a variance component. And to show you a little bit more, and this begins to answer perhaps what Richard's question is. I have some more stuff at the very end. But the key to the components of the prior for HBART, right? For the mean, we do just what we did before. First, we center y at 0, okay? And then we set the means to be IID from some normal, which means that f of x, right? That f of x is itself going to be, if I integrate out the mu's, is going to be normal with mean 0 and m times this variance that I use there. So basically what I want to do is I want this variance, this m sigma squared, to be tau squared, to be like the variance of y that I observed. And then so that means that tau squared is equal to the variance of y divided by m.
So how do you choose m?
Oh, we just typically pick around 200, but we try different things. But no, but if you chose 100, you would be using a different prior. So as you do it, you know, for each choice of m, you change the prior a little bit. So the prior does depend on m. But we found that for, if you look at plots of performance as m gets really large, your performance, predicted performance, tends to be terrific and deprecates only very, very slowly. But when you make m small, you can start doing the variable selection. So m is a parameter you can play around with. Some people have thought about putting a prior on m, and you could do that too. And then for the MCMC, what you'd have to do is be slightly changing the prior whenever you changed m a little bit. I think it's doable, but
you would expect some overfitting if m gets too big. I mean, if you look at the out of sample prediction or so.
if m gets too big, so what you see is one of these, are they called ski plots or something? Scree plots, where the performance gets really good as you add trees, and then as you add more and more, it slowly starts to get worse. But it's remarkable how you just tend not to overfit. Anyway, of course you have to take my word for it. What a good guy. Here, by the way, the variance component prior is, we have these bottom node variance components. We're using an inverse gamma prior, so that works. It's not quite as good, but you have to use another heuristic for the way to calibrate with the variance. But it seems you can all do that, and the simplicity of the HBART MCMC is maintained. In fact, I'll show you the HBART MCMC algorithm seems to, we have to enhance the Metropolis proposal, but it seems to converge very, very quickly. This is, you know, just time and time again, this thing seems to work. This is the draws of sigma in BART, but if I go to HBART, well, I have different sigmas, so I can just look at all of them, or I can look at the average. But there are many ways to sort of convey that it's doing okay. And this is just a summary of, you know, getting your MCMC stuff. You get your output, and you can average your draws to get estimates of f and sigma squared. Let me show you more examples because it's more fun. Here is a simple one-dimensional example. And now, because I have my variance function here, I now can estimate not only the mean, but I can estimate, you know, you like 2 times the standard deviation. And these are pretty good estimates. This is a plot of the data. If I took this to a separate plot, now I've got, here is how the mean depends on x, and here is how the variance depends on x. And these are uncertainty intervals around that. Okay. Let me show you 2 displays that come out here. I think these are kind of new regression diagnostics that come out of this setup. Okay. The first one, and it's a simple idea, but given your x, given an x, you can now sort your estimates of the variance, okay, from smallest to largest, and then plot the 95% quantile intervals for S versus S has X. So where do you think the variance estimates are? And you can see that here, right, these are the smallest ones in your data set, and these are the largest ones. And this is now the ordinary BART estimate of sigma. This is what it would be. And so you can see that I'm getting a lot of small estimates of sigma here and a lot of large estimates here. It's a way of quickly gauging whether or not I've got heteroscedasticity in a So you can just quickly apply this thing, and it will automatically tell you not only the mean level, but do you have a potential heteroscedasticity problem. A second diagnostic here is, and this is more subtle, is this is using a QQ plot to evaluate things. So what you do is for each of your draws, okay, so I've got a particular point, and now for each of my draws, I can now sample from a normal, and I can compute quickly, right, the quantile of my data within the draws. Okay. And so if the model is right, if I really have normal data around my function, the quantiles should look like draws from a uniform distribution, and you can gauge that with QQ plots. So here you can see, right, that you're using QQ plots are suggesting that HBART is really giving you a much better model of the distribution of Y than BART is, than the actual Y. BART, the homoscedasticity assumption is really holding the distribution back from the data that you've really observed. Notice this is quite different than people often use RMSE evaluations, but this QQ plot is a distributional. You're looking at a distributional quality. Right, and this is the point that I just made, right? For numeric responses, we typically check RMSE, but we're getting a full predictive distribution. So with the QQ plots, we're assessing the full distributional fit. Now, here's just some real examples. So nice and relaxed. I've got a real example with 15 predictor variables. Okay? So I've got the price of a used car, and now I have characteristics of the car, whatever. So, you know, you could run a multiple regression, linear regression on this fine, but we're going to do it non-parametrically, estimating both the mean and the variance of the price as a function of the 15 variables. Okay. And immediately, we get to see that, hey, there's substantial heteroscedasticity here. You definitely don't want to use a sort of homoscedastic regression model. Okay. In fact, just over BART, the QQ plots show a clear improvement. It's not perfect, but it's pretty good. Okay. To get going with this. We can, well, I'll just say quickly, there's a key prior hyperparameter when you're selecting that calibration going in, and you can actually use different e-distance measures between empirical quantiles and uniform quantiles to sort of judge. It's basically trying to make the QQ plot even better in your selection of hyperparameters. And here at BART, it's one way to do it. HBART, you can see that it's better. I don't have time really to explain this plot, but this plot is actually kind of interesting. Remember I mentioned variable selection? Well, you can do the variable selection here to see what variables really matter of those 15 variables. And if you look at the number of node splits, you get to see that these two variables matter as for functions of the mean function. But for the conditional variance function, you actually find that not only do those two variables matter, but there's another variable that's actually really determining the conditional variance. So there's two important functions here, and you can use BART to sort of to find what that structure is. Okay, two last examples, quick ones. This is a fishing example where you're just measuring what your daily catch is. So Y is the daily catch of fishing boats. There are 25 explanatory variables, okay? And you get to see there's heteroscedasticity here immediately, okay? This is clearly not the right model to use because Y here we know is strictly positive. So you could model it in a more refined way, but it's still fine to use BART here. It seems to work pretty well. The last example is number of alcoholic beverages consumed in the last 2 weeks. This is for people, I guess, who are trying to stop drinking. And there are 35 explanatory variables here, okay? that we put in, and it's just a regression, but it's kind of cool. It looks like there's no heteroscedasticity here. Okay? There's not enough evidence that maybe a homoscedastic model would work quickly. But this is just a quick check to see if you're going to have to take care of heteroscedasticity in your model. There. Okay, so the last remarks, boy, good timing. As I said before, this stuff is crying out for theoretical support. Lots of people are doing BART and whatever. One piece of recently, Veronika Rotchkova and Stephanie Vanderpass got a posterior concentration result showing near minimax posterior concentration for certain classes of Holder functions, but there's lots more to do. There's, anyway. And software for BART, just for the record, it's on CRAN for MBART. I don't even know what this means. Rob told me to say this. And HBART is coming soon as Lisa BART, right, from the BART Simpson family. Anyway, that does it. Thank you very much.
I think we're actually being kicked out of here at 11 today. So any quick question for
You showed very nice monotone
Yes.
results. Can you do the same thing with convexity?
Oh, well, you certainly can divide, you can decompose a function into its convex and non-convex part. It's something we've thought of, but we haven't really. So I don't know how to make it. I think it's going to be more difficult to make a tree convex. I mean,
yeah, I was thinking about doing
Yeah,
that
yeah,
at the
yeah.
top, and it's really quite complex.
but it's a great
Perhaps
question.
I'll talk to you about it.
Okay, good, thank you. Good idea. And
can you do things with generalized additive models rather than just additive models? If you've got a transformation in there and you've got some binary response or something like that.
I don't see why not, actually, so we haven't tried that. By the way, one thing you could do here also is you could transform Y and maybe get an even better response, which is sort of the idea of that. But yeah, I wonder, haven't even thought of even single index models maybe, and stuff like that. Yeah. So good to give it here. Now you guys are gonna give me millions of ideas, I'm sure. So terrific. Thank you.
Thank you very much, everyone.